Hi, I want to say good morning, good afternoon, or good evening, depending on where you are in the world. But that said, today is the 20th of December 2024, and this is the ZP weekly webinar. So we've gone, admittedly, maybe almost 12 hours late now. But that said, that's because I've been done a lot of traveling, and I've just got back, and I was pretty jet lagged. But that said, let me go forward. So the question today, we're going to talk about multi-analyte detection. Somebody has sent through a whole list of analytes, and most of them are actually really quite achievable. In fact, all of them are, and that's because there's something called a comprehensive metabolic panel. When you have some blood taken at a hospital or something, there'll be like a list of sort of 14 things that they will otherwise test, and this is this sort of metabolic panel, and the compounds that this, or the analytes that this person's interested in, are really all drawn off that panel. So that means it's simple. It's not like you're trying to do something that's never been detected before. You're actually trying to do something to detect that has been detected before, and therefore it is easier to do. Just need a different form factor. Question number 2 is about, we've got something called the Anapot EIS. Actually, it's a good point. Actually, I'm going to also, I'll do a demo today of a new potentiostat called the Sensor. This is a real game changer when it actually comes to less doing hardcore electrochemistry and more, though it does do hardcore electrochemistry in terms of it can do amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, square wave voltammetry. The QR codes will become apparent later on in this talk. But anyway, they've got what's called an Anapot EIS, and they want to know about interdigitated electrodes running in a generator collector mode. And I will talk about that. I've got quite a few slides on that. So that's question number 2. Question number 3, linear differential pulse voltammetry. I do have some slides on this, and I am going to answer the question, but I sort of do think when I was doing it now, I was thinking, right, well, I'm running out of time now, and I need to do this webinar, but I think I can do a better job on this. The nice thing about, always being active in electrochemistry, I think my own understanding gets deeper and deeper over the years as well. The nice thing about ZP is when we talk about these things, we talk about them from a perspective of actually doing them quite a lot, and talking about them, doing them, seeing how these techniques and etc. really work in in real assays. Let's say pH sensors. Somebody wants to know about what nasties do we have that will leach out. The quick answer is I don't think we've got any nasties that will leach out. And the reason I mention that is because they're kind of cute. Yeah, they may be using it in the delivery of pharmaceuticals. I want to be very clear that when we sell things like pH sensors on our website, they're for research purposes only, because it's a really, I really don't want people incorporating our technologies, let's say, into a final medical device, and I know nothing about it, because it's the same with, if you go on Merck and you buy kind of chemicals off Merck. Merck used to be known as Sigma Aldrich, but they got bought by Sigma Aldrich. If you read their terms and conditions, you actually find out that what they're selling you is for R&D purposes only. It's an important point, because many people do actually use their materials in products, but actually you are only meant to buy them for research purposes only, because they're really probably worried about the liability of their materials ending up in medical products, etc. And it's the same for us as well, that you can buy products off our website, and you're perfectly welcome to use them in R&D, but really if you're going to start incorporating them into a medical product, then you need what's called a quality agreement with us, and we will only do those really with well-funded companies, etc. But you're welcome to buy them for R&D purposes only. But the quick answer to your question is I don't think there are any nasties that are going to get out there but into the solutions, but you will have to check. Question number 5, detection of Diazinon. I am a chemist, so I should be able to spell this better. Diazinon. That may be a better pronunciation of that. This is an organophosphate that's used in sheep dip, and it's probably to control, I want to say insects, but things like probably lice or something in sheep. And I'll talk about the detection of that. I'll also very quickly talk about molecular assays. In molecular assays, you often have an RNA or a DNA strand that may capture another RNA or another DNA strand, and I will talk about the detection of that binding using intercalation techniques, where you take a dye like Meldella blue, and Meldella blue can intercalate into these kind of molecular hybrids, or this hybridization between two DNAs, and give you a signal. I'll talk about that. I'll talk about lactate sensors, and I'll also talk about glucose sensors at the end as well. All right, so there's enough waffles going through those questions. Just to say that we do have a webinar on the 22nd of October. If you are interested in doing an assay that you would like it to go to market, or you would like it to be more impactful than is normal, then that demo on the 22nd of October should be super interesting to you. And it's probably worth saying that we're going to have some other webinars. If you're let me just click down. We're doing one on wearables. So in front of me, in fact, I do have a wearable actually in front of me at the moment. I'm going to today's not heavily onto wearables, though I am going to talk about implanted lactate sensor briefly. But this is a wearables microneedle array from ZP. This is not something that we sell on the website. I mean, I have talked about it. It's just that when I say on the website, because it's had a lot of investment in it. It's got 50 patents on it, and our business model on this is actually to license it into well-funded startups. So, but we do have a webinar on wearables on the 5th of November, and probably I'll talk about that in more detail there. So, any links, by the way, will also be underneath this video when it's gone live. We're also doing a specific webinar for academic researchers. I think this might be super useful to people who are, if you're watching this, you're academic and you're more interested in some of your research becoming more impactful, then we'll definitely do a webinar on the 23rd of October. Now, if you're watching this after the 23rd of October, or after the 5th of November, or after the 22nd of October, don't worry, because the links will take you to the next, let's say, webinar in the series. So on that webinar on the 22nd of October, when we're talking to our academic colleagues, we'll talk about our screen printed electrodes, we'll talk about our Sensor All platform, we'll talk about the amperometry, the open circuit potentiometry, the impedance spectroscopy, the linear sweep voltammetry, the cycle voltammetry, the square wave voltammetry. And I'm also going to demonstrate it today, actually, this data pipe, where we can actually then, using these techniques and what's called a data pipe, we can actually turn it into final concentration. And this is the bit that really kind of closes the gap between what academia does and what can become a product. So we've got chili, ginger, pH, nitrate, total antioxidant capacity, glucose, potassium, testosterone, lead has just been added on there, and also something called NADCC, which is used in water sterilization. Anyway, if you're an academic and you're interested in electrochemical biosensing, then I would definitely of course I'm biased, but I definitely recommend you come to that webinar. And again, if any links pop up on this particular video, let's say, then I'll put those links underneath this video as well. Just to say, we're also going to have in-person live workshops. We did these, but I don't think we've had a live workshop all year. So in fact, we've almost probably been a whole year now without a live workshop. But we are going to have live workshops on the 20th and the 21st of November. These will be, let's have a quick look actually, I've got the details here. It's on wearables, and it's also on point of need testing. Most people who come to ZP are talking about point of need testing or wearable biosensors. It will be in Norway. It will be on the 20th and 21st of November, and it'll be led by me. I should say that it's super focused on doing practicals as well as doing lectures. It's easy to give lectures and stuff, but actually we've got labs, and so we can actually take people in the labs and do lab work and demonstrations. So you learn really by doing, which I think is it is the most effective way of learning. So question number one, first of all, it's probably worth saying that ZP, we probably have one of the biggest range of biosensors that's kind of on the R&D market. So if somebody wants to make a quick proof of principle, we have lots and lots of biosensors. This person is interested in HbA1c. This is what's called a glycated hemoglobin. If your glucose levels are kind of low, then you may have a sort of glycated hemoglobin of like 4%, which means that 4%. I think it means of the hemoglobin is kind of being glycated. And if you've got when I say a lot of diabetes, if your glucose levels are quite high, which is hyperglycemic, then it can sort of really load up, and you can get above 7%, 8%, 9%. So he's interested in understanding the glycated hemoglobin. That's quite a standard lab test these days, so it's very sort of achievable. We haven't done it at ZP. I have done it in my lifetime, but we haven't done it at ZP. So, but we do a lot of contract development, contract manufacturing work. But it's probably worth saying that, you know, doing contract development, contract manufacturing with ZP, if you're in academia, it's really what you should do. And if you're a startup company, then, you know, it's good to come to us. Even if you're a matured company, we're quick to do that kind of thing. The other thing they want to do is hemoglobin. Hemoglobin is, you know, every year hundreds of millions of hemoglobin tests are done. So this is a very kind of doable assay just because there's so many. Bilirubin, this is obviously important in, I want to say juveniles, but really young babies. And it is actually an assay that we have done at ZP. It's not on the web store. We've just done it for other companies. Uric acid is actually an assay that we do have on the web store. So is creatinine. Cholesterol we don't, but there are sort of hundreds of millions probably of cholesterol tests done per annum. So it's quite a straightforward test to develop. Albumin is also the same as well. You want to do on 2 to 3 drops of blood. I'll do an assay in a minute, which is half this volume. So why is electrochemistry so good? Because you can use quite dirty samples on it. The technology can be quite low cost, and it really requires one of the smallest volumes necessary. When I think of all the modalities of test in the world, electrochemistry can easily do 300 nanoliters, you know, which is an order of magnitude, no, 2 orders of magnitude even below what this gentleman is asking for here. And he wants a prototype. When people say, oh, with a 4 to 6 error margin, you know, most glucose meters on the market have a 15% error margin. So you really do have to kind of understand what it is you're asking for. That if you're asking for 4 to 6, you may have to ask yourself the question, is that what the market's demanding? You know, and then actually, you know, the good thing about ZP is we can actually put these sort of requirements within context of what's actually on the market already. As you saw, I was able to tell you, you know, all these tests are already done. People want to do it because they want to then sort of do it in a point of care and a low cost in a distributed manner. So I can see where the value is coming from, but as actual tests, they're all quite doable. And then just even looking at the error, you can then put it in context and say, okay, 46%, yeah, sure, it's doable. Especially because most of these are actually in quite high concentration. But of course, it's not what you need, it's what you can actually afford to develop and at what time can you afford to develop it. So for example, if your investment is 3,000 euros, you probably can't afford to do any of this. But if you're 30,000 euros, then you can start biting into this. It's 300,000 euros, you can bite into a bit more. If it's 3 million euros, you can bite into a bit more. So sometimes need and what you can do depends on the budget that you actually have available. It's probably worth saying at ZP, we do have a lot of experience of actually not just doing single tests at a time. We actually do have clients in where we're doing parallel testing. So we're able to test up, you know, you sort of have a drop of blood. But this drop of blood is probably 50 to 100 microliters. And here we're doing sort of 3 tests in parallel, different configurations. You can see the way it's capillary filling. So ZP, we make a really good low cost way of making a microfluidic. And the same just in the final design here as well. So we're quite fast to iterate and do these kind of designs. And also this guy might want to be doing something like, maybe I should have counted them up. I think it was about 6 to 8 assays. So this is 6 assays in a row. So we do have these kind of programs, and we do these kind of programs with clients. I want to say all the time, basically. Question number 1. You can also do a very quick proof of principle just on this potentiostat. This potentiostat can basically do, if I grab my phone, in fact, this is a really smart way of doing potentiostats, I would say. What I want to do is, I've got my phone here. My phone at the moment, if I want to do amperometry, I can scan that QR code and now I'm in amperometry mode. If I want to do open circuit potentiometry, I'm now in open circuit potentiometry, and I'm in Bluetooth connection because it says device connected with this, and actually so I can run any of those assays on that. So it's a really, it's a very different type of potentiostat. I mean, it doesn't look like a potentiostat. You know, in fact, you know, it takes electrodes from ZP. I'll just plug them in. There we go. And in a bit, I'll actually do a quick demo on that as well, so you can sort of see that in a bit more detail. The reason I bring this up is because sometimes if you want to get a minimally viable prototype, using this rather than kind of going for all 8, you know, if you want to show something to an investor or something like that, this kind of technology is much more believable. Otherwise, you're trying to build a parallel system from the start just to get some sort of funding, and you're kind of putting quite a big gap between you and your ability to raise money. So you can do amperometry on this, you can do open circuit potentiometry on this, you can do impedance spectroscopy on this, you can do linear sweep voltammetry on this, you can do cyclic voltammetry on this, and you can also do square wave voltammetry on this as well. And square wave voltammetry will become interesting in a bit, because we are actually going to talk about differential pulse voltammetry in this today. So what's different about this device is we can basically go from any of these amperometric techniques, these electrochemical techniques, go through something called a data pipe. So we do have a system called Julie, and I will be using Julie shortly. And in fact, we can send all of our data up to the cloud. We can process our data up in the cloud, and essentially go from, how do I put this, from raw signal to concentrations, as I can do here. And I'll talk through this shortly as well. So let me just click there and just go here. So there is a data pipe. It exists in the cloud, but this system actually automatically sends the data to the cloud. And then we've got these other QR codes then that mean once the data's gone through a data pipe, you can actually turn it into something meaningful. So by meaningful, analytes or analytes or concentrations of analytes in a kind of meaningful manner. So we've got, if I just click down, we've got chili, ginger, pH, nitrates, total antioxidative capacity, glucose, potassium, testosterone, NADCC, 2 of those because we've got the assay available in 2 modalities. And we've also got lead as well. Interestingly, actually, yeah, because of this QR code system, we actually have quite a lot of flexibility with this system. So when I said we've got NADCC in 2 modalities, is because we're doing it with and without calibration. We're basically going to let the end user try out 2 QR codes and just come back with us and give us some feedback as well. And then lead in water should be an exciting one, I think. Just FYI, if we don't have the biosensor for you, or you're more of a biosensor developer rather than a biosensor adopter, it's probably worth saying we do have all these screen printed electrodes. In fact, I will be talking about a few of these more in the webinar as I go forward, especially that gold one. I'll be talking about molecular assays shortly, and also this 501 carbon. I'll be using this when talking about interdigitated electrodes very shortly. Crumbs, that was only question number 1. So question number 2, okay, we got to go a bit faster on this. All right, question number 2. So somebody has an anapot. They've got an interdigitated array. I must admit, I've been referring to them as an IDE and interdigitated electrodes, but interdigitated array. They want to, it works perfectly well as well, and they want to run it in what's called a generator collector mode, and I will essentially talk about that as we go along. I'm going to do a bit of a background on this. I'll be a bit pedantic on this, but that said, I'm thinking I'm going to use the idea of the oxidation of ferrocyanide to ferricyanide to help me think this through. So if I do a cyclic voltammetry on ferrocyanide and quick plug, this device will definitely do, where's cyclic voltammetry? That was square wave. That's cyclic voltammetry. So this device will definitely do cyclic voltammetry. So first of all, I'm just thinking about cyclic voltammetry to start with. So using cyclic voltammetry, I may work out that the oxidation peak for ferro to ferricyanide is like 100 millivolts. And it may be reducing versus is about 0 millivolts. That's versus silver chloride in a about 135 millimolar chloride solution. And there's the details I just waffled out there are not so important. Now what they're describing is they're talking about a generator collector mode. So what is going on here? What are we all talking about? Okay, so I've got this electrode and I've got some ferrocyanide on there, and I oxidize it to ferricyanide, and I kind of know that approximately the oxidation potential is about 100 millivolts versus the reference, because I did a quick cyclic voltammogram on that earlier on. Now I've done it here like it's what's called a line electrode or a microelectrode. When you start getting down towards microelectrodes, you don't necessarily have the classic voltammogram or cyclovoltammogram that you would normally expect, because now you're in a kind of in a very different diffusion regime. But I've done it doesn't matter whether you get the classic voltammogram or you get something that's more for a microelectrode. You get some current as you do a voltage sweep on this, and that's the oxidation of ferrocyanide to ferricyanide. But let's say you've got an electrode fairly close to this. Then in fact what you can end up having is diffusion across of that ferricyanide, and if the potential is correct or not correct, is set or happens to be at the right potential on the collector, you can end up reducing the ferricyanide back to ferrocyanide, and then it's maybe free to diffuse back to the generator. So when the person's asking about generator collector and IDEs, well, they said interdigitated arrays, but it's the same thing really. You've got a generator, you've got a collector. We're generating ferricyanide at one electrode, it's diffusing to the other electrode where it gets reduced to ferrocyanide, and then it's actually diffusing back to the electrode, and that's really like a feedback loop. So what does that mean then? That means that you can end up with a current that's higher than you were otherwise expected, because in fact the material that you're consuming at your generator, because you're producing a product which is ferricyanide, is actually recycled essentially, and in fact you get more current because of the regeneration at the collector of the ferrocyanide. Now the more current you get is dependent on the efficiency of this process. If these two electrodes are closer to one another, then you can imagine that the efficiency is higher, and if they're further apart, then the efficiency will drop off. And you can imagine that, you know, the reason it drops off is because when you're close, you generate and you detect, you generate and you detect. When you get further and further away, you're generating, but some of it actually doesn't get back to the original generator electrode. It actually gets lost in just the bulk solution. So I've kind of thinking this through over the years, I realized that small, thin solutions and close together electrodes probably amplify this feedback loop. Now, what I've put in here is just put a reference electrode in here, because I'm talking about sort of essentially holding one electrode, in this case at 100 millivolts, and maybe the other electrode at 0 millivolts. I got those values off the simulation of the cyclovoltammogram that I'm running on the right hand side. So those weren't just plucked from anywhere, and you set the potentials at those. Essentially, I'm acting like two working electrodes here. So to balance this off, I actually need a counter electrode. But I don't think this person's actually describing this, and I think they're actually describing a much more simple electrode array. But this is definitely a way of doing generator collector with IDE, but it's quite complex because you've got at least 4 electrodes involved here. I've got a few more slides on this, so let's dig into this a little bit more. And by the way, the current that you're getting at your collector electrode is probably the same as what you're getting at your generator electrode. I say probably the same as. It's never going to be less than. It's sometimes maybe, I don't want to say it's going to be more than. In fact, it's going to be the same as, because I'm just thinking about, is that really true? I was just thinking about a normal 3 electrode system, but this is not a normal electrode system. So it'll probably be the same as, or a little bit more depending on efficiencies. Right, so let me stop for a second. So this person's asking, will the anapot, EIS, be able to run my IDA, my interdigitated array, or my interdigitated electrode in a generator collector mode? I'm going to say yes, but this is a very nuanced answer, right? So let's get to the nuanced answer. Just as a side note, I'm not a big fan of rotating ring disc electrodes. I appreciate that rotating ring disc electrodes are actually more useful for people who are doing sometimes electrochemical engineering, where you're thinking about scaling up electrolysis, and they may be more useful for people who are generally interested in kind of mass transport techniques. But for biosensor developers, they kind of hold you back. Now the reason I think they hold you back is, I'm just going to make a side comment here. If you're going to develop electrochemical biosensors, develop them on instruments that look like the product you're probably finally going to release. When you do use hardcore analytical setups like this, it's really taking you away from the point of care sort of diagnostic, or even the wearable. I've got a wearable on my wrist here. It's taking you away from the final product. And so it's kind of, you could gather loads of data, but it's not very sort of, you know, translating all that data then back onto the product that you're really trying to develop is pretty tough. Right. So we've got a rotating ring disc electrode, and if you really look at it in a rotating ring disc electrode, you often have a generator electrode and you often have a collector electrode. Just a side comment that even though we're talking about IDAs or IDEs, depending on which acronym or how you want to call them, this concept of generator and collector is broader than just IDEs. They're also, it's probably the same in ring disc, well, it is the same in ring disc electrodes. Now what this person is describing is an interdigitated electroarray, and they're not, well, first of all, you can have interdigitated electrode arrays where in fact you've got, and I would call this active, and I'll tell you why I call it active in a minute, because in this one you've got a working electrode 1 and a working electrode 2 and a common counter with it and a common reference. So I would call this pretty active, because what I mean by that is you're actively controlling the potential on the working electrode, and you're actively controlling the working electrode on, the potential at the working electrode number 2. And the anapot EIS will not do that. The anapot EIS is a 3 electrode potentiostat. It will do counter electrode, reference electrode, and working electrode. But I got a suspicion this person's actually not really thinking about having 2 working electrodes, a counter and a reference. I wonder if they're actually thinking about getting rid of the counter and reference, having this kind of array like this, and in fact not having the working electrode 2, but having that as actually a reference and counter. That's more commonly done. When people talk about interdigitated electrodes, they're often talking about really 2 electrodes that are interdigitated, and in fact one of the electrodes is really acting as a reference and counter. In that particular case, this potentiostat will work. And depending on the chemistry that you're doing, it will actually work in a collector-generator mode. And what I mean by that is, so I say that if you want to run 2 working electrodes where you're independently controlling their potential, then the EIS will not, the anapot EIS will not do that. But the anapot EIS that you do have will do it when, in fact, you've taken away the reference and counter, and you've just made the second working electrode, in fact, be the combined reference and counter. Now, the active mode is good because it gives you control on both the potential on both working electrodes, whereas this passive mode, where you essentially get rid of the reference, you get rid of the counter, and you combine the reference and counter on the reference and counter on the second electrode. Actually, it will run that mode, and it's non-controlled, but I actually got a suspicion it will work for you. But I don't know your chemistry, so I've sort of said here that if you set up this system where you've just in fact had 2 digitated electrodes, so let's say they were both gold, and you were oxidizing ferrocyanide to ferricyanide on the working electrode, on the collector electrodes, which is really the combined counter and reference, in fact you would end up reducing ferri back to ferrocyanide. So it's passive, but it would work as a generator collector, because in fact you had something like, let me make up the solution in my head now. So I would say that, you know, if you had sort of 5 millimolar 5 millimolar ferrocyanide in there, you would end up generating ferricyanide. It would diffuse across, you would be collecting it, or regenerating rather, the ferrocyanide, and it would probably diffuse back across. So the nuance of me saying whether the anapot EIS can be made to work in a generator collector mode does depend a little bit on the electrodes, and it also depends on the solution that you're using. But if it was a simple system like 2 gold electrodes and a ferrocyanide solution, then it probably would be running in a generator collector mode. So the short answer is no, it won't work in the sort of active mode where you've got 2 working electrodes that are independently controlled. But in a passive mode where in fact you're only controlling one of the working electrodes and you're not entirely certain what's happening on the other electrode, it probably is doing the chemistry that you desire. But that depends on what chemistry you're actually putting into the solution. So something like ferrocyanide is very reversible. So it probably is actually doing the, if you're doing an oxidation on one electrode, it'll be doing the reduction on the other electrode, and you will get that feedback loop. All right. There's something, sometimes this is just made me think a little bit about unexpected feedback loops that can sometimes happen. Now, this is not really that person's question, but this is just something that I want to make people aware of. So at ZP, so for example, we're really talented in making really good screen printed electrodes. Why are they so good? It's actually the repeatability that makes them so good. Why are ZP screen printed electrodes so repeatable? Because I use them, or we use them, let's say, in our own products. We make products with these. We ship products all around the world on these. It's actually a feedback loop built into the ZP business model, where I will sell screen printed electrodes, but I actually use them myself. So you can understand that I have a quality feedback built into my systems. It's not, when they don't go right, the screen printed electrodes, the first people to know at ZP is ZP. So you don't come back and tell me that the screen printed electrodes are not working right, because if they weren't working right, we would have known months before you ever actually got anywhere near them. They wouldn't have been able to leave the factory, because we would have failed them for our own internal usage. Anyway, so that's a business feedback loop. Let me get back to a feedback loop on screen printed electrodes. So here's the screen printed electrode. Let me put a drop of, say, ferrocyanide on this screen printed electrode. Let's say that drop was 50 microliters. That's probably what's happening on these electrodes on occasions. And I can talk about other scenarios as well. Is we're oxidizing ferrocyanide to ferricyanide, and around the edge of this, we've got this counter electrode. Well, what do you think is happening on the counter electrode? Nobody ever asks themselves what's happening on the counter electrode. Well, if I'm sitting in a bath of, if I'm sitting in a bath of ferrocyanide, in fact, if that bath was a 50-50 ferricyanide and ferrocyanide, then maybe the argument I'm about to make would be stronger. But I'm saying that what you could be happening is, on the working electrode, I'm generating ferricyanide by the oxidation of ferrocyanide. Ferrocyanide diffuses to the counter electrode. What's the counter electrode going to do? Oh, in fact, it's going to end up reducing ferricyanide back to ferrocyanide. And that ferrocyanide will diffuse back to the working electrode, where it will be generated ferro back into ferri. Ferri will then diffuse across to the counter electrode, where it will get reduced to ferrocyanide. This is also a loop system. So people, I think, sometimes in their research with screen printed electrodes probably don't realize it, but there are definitely scenarios where, in fact, you're doing a accidental generator collector experiment, and probably the longer that experimental run is, let's say it was amperometry, the more likely you are to do this. If you did a quick cyclovoltammogram at like 100 millivolts per second, with a potential range of like plus or minus 500 millivolts, you probably won't have time to set up this. But if you're doing a longer amperometry experiment, then you probably will find that you'll actually get this feedback loop. And in fact, I have talked to other scientists, and I have done this myself, where in fact you're doing amperometry and the signal's dropping off in a Cottrell fashion, and then after some seconds the signal comes up a bit more. And that's actually because the material is starting to back arrive from the counter electrode to the working electrode. So I have seen that, especially in these kind of ferrocyanide systems. Right, so I then need to finish with the last slide, because this is only question number 2. So sometimes people are getting more current in their screen printed electrode experiments than they would otherwise imagine, because they don't know about this potential opportunity for feedback loops. But it won't always happen. It's maybe only sometimes really experienced people, dare I say it, like ourselves, that would actually spot these phenomena were actually going on. Now, this particular electrode won't have that feedback loop, and I'm just going to explain that now. So if I took that electrode and I put a drop of ferrocyanide on it, at the working electrode, we're probably oxidizing ferrocyanide to ferricyanide. Our counter electrode is actually silver chloride in this case. Now, what would happen at our counter electrode then? Well, in fact, our counter electrode forms silver and chloride anions. So because the reduction of silver chloride to silver is actually very facile, very easy. We also have quite a lot of it in our electrode. So the dominant reaction in this particular case at our silver chloride electrode is not necessarily the reduction of ferricyanide to ferrocyanide, and therefore causing a closed feedback loop. In fact, the electrode's already given a facile reaction. It's a reduction of silver chloride to silver with a release of chloride. And before you start going, oh, well, there you are, you've got this new species. Yeah, we're often doing this kind of work in buffer solutions. And if you look at things like PBS, phosphate buffer solution, the chloride concentrations are actually quite high in these, like 135 millimolar. So the little bit of electrochemistry that you're doing will hardly disturb the chloride concentration. I've done these kind of calculations. They're not very hard. It's called Faraday's law of electrolysis, and you can do them and sort of think, how much chloride am I really producing to carry that kind of current? And it's really not that significant amount compared to the amount of chloride that's actually in solution. So this is a way of avoiding the accidental feedback loop that I think people sometimes have, and they definitely don't always realize it. Question number 2, you were asking, can the Anapot EIS run that IDA in a generator collector mode? Not actively, but passively it probably can, but not actively. It's not a bipotentiostat with essentially the independent control of the potential on those two working electrodes. That was a long answer for a fairly short question, but at ZP, if you ask a question, you're going to get the answer. I do have a short the gentleman is asking about pH sensors. I will have a short answer for you. Question number 3. Oh, this is a hard one. I want to learn about linear differential pulse voltammetry. I think I can still make a better job of this. If you ask me this question every 2 years, I'll make a better and better job at all of these things. But there's lots of voltammetry out there: linear sweep, cyclovoltammetry, square wave voltammetry, differential pulse voltammetry, normal pulse voltammetry. And in fact, a quick one again. So we do have. So I've got this in cyclovoltammetry at the moment. I can put it into linear sweep voltammetry at the moment. So we do have square wave, cyclovoltammetry, linear sweep voltammetry. A technique that complements sometimes square wave voltammetry and differential pulse voltammetry is impedance spectroscopy. This is an interesting technique. It could argue sometimes it's too sensitive. But that said, let me dive back to the slides now. So you had a very specific question, which is talk to me about differential pulse voltammetry. So let's talk to you about differential pulse voltammetry. First of all, there's a bit of a lineage here, and with the lineage is that why do differential pulse voltammetry and square wave voltammetry in particular exist? And well, they exist because if I'm trying to do the oxidation of ferrocyanide to ferricyanide, I've got this solution on my electrode, and I turn my electrode on, or I change the potential. Every time you change the potential, so linear sweep voltammetry, square wave voltammetry, differential pulse voltammetry, cyclovoltammetry, voltage never ever changes these days in a linear fashion. Most electronics these days are actually digital, so we're really changing the potential by little potential steps. You know, maybe these potential steps are only 5 millivolt potential steps, so they're pretending these electronics are pretending to be digital, pretending to be analog, when in fact they're digital. So what happens when we do these little digital potential changes? Well, in fact, we get a oxidation of the ferrocyanide to ferricyanide, and we get a little rearrangement of the ions near the electrode. So the rearrangement of those ions is called a charging current, and then we also get a bit of a current due to the Faradaic process, which is the oxidation of ferrocyanide to ferricyanide. But what electrochemists don't like is they don't like the charging current, because they say that's not my electrochemical signal, that's an electronic signal due to the rearrangement of ions. I think we're going to change our opinion on this in the next few years, actually, because I think data science techniques now means that we can actually extract useful information from the charging current, where in the past we would have thrown it away. I actually think that's less of a case going forward. But today, a lot of electrochemical experiments do throw away the charging current, but I actually think it contains more information than useful information, actually. But today, the tradition is to be throwing it away quite a lot. So all these techniques, square wave voltammetry and differential pulse voltammetry, they exist to actually get rid of this charging current and also to get rid of the background current. So the two strategies that sort of go on in this life is timing. So if you do a potential step, if you just delay the reading of the current by a few milliseconds, then you can diminish the effect of the charging current. So just delaying or playing with timing is one way of getting rid of charging current. The other way of getting rid of charging current is to play with timing and also to do a subtraction. So differential pulse voltammetry and square wave voltammetry tend to play with timing, and they also do subtraction. I'll talk about square wave voltammetry and then differential pulse voltammetry now, and talk about this subtraction. So in linear sweep voltammetry, they only really play with timing. I said to you, there is no true analog device anymore where, you know, if you go from 0 to 200 millivolts, you used to be able to do it on an analog electronic set that was probably truly analog, that, you know, you were sweeping. But these days you're doing tiny steps. Like I say, these steps may only be 5 millivolts, so it's quite small, but all the same, it's steps. And every time you change potential, you get a charging current. So what they do in linear sweep voltammetry, and this will also be applicable to square wave and differential pulse voltammetry as well, is you take these little steps, they wait a few milliseconds and they take a reading. They take a step, they wait a few milliseconds and they take a reading. They take a step, they wait a few milliseconds and then they take a reading. And so what you're really looking at is time filtered current, because actually they've left out about 50% of the initial current, because they called that they said that had the charging current in it. At this moment, you have less control on that in the potentiostats. At ZP, I'm really thinking about this a bit, you know, is how we sort of open this back up again, because I think actually there's so many, all of us now are really just becoming data scientists. Now my conduit for data might be electrochemistry, but I may have to I should really think of myself as a data scientist. I've got to be careful with that term. So I'm an electrochemist, I'm also an analytical chemist, and I should also think of myself as a bit of a data scientist as well. And we should all think more broadly rather than just being constrained by the way we're actually trained. So this is a side note, but I actually have to think about this quite a bit myself as well. As, are we losing something by essentially time filtering this out of the signal? And the answer is we probably are losing something, but by not filtering it out, we're then adding complexity in again. But now people are getting much better at dealing with data, because everyone is effectively, should be a part of their job description should be data science. Right, square wave voltammetry. So in this one, they don't just do timing filtering, they're basically doing subtraction as well. So they're sort of pretending that we got this simple staircase as you do have in linear sweep voltammetry, except they make the waveform more complex by adding this this kind of waveform on top of that. So in fact, they're generally increasing, but they're going up, they go down, they go up a bit more, they go down a bit less, they go up a bit more, but they come down a bit less. So basically the potential is going up and down, up and down, up and down. And they're actually sampling in 2 places. So they're they've got something called the forward. So I sample here. So I'm timing, because in fact I didn't collect the data at the beginning of this pulse. I collected it near the end of this pulse. And it's the same with the reverse, forward and reverse they call it. And I'm also filtering by timing, because in fact I collect at the bottom, at the end of this 50%. And it's not just timing, they're actually averaging as well. So when you sometimes see this data, it's effectively been through a couple of filters. One of them is a timing filter, and the other one is an averaging filter. And I don't think people really realize this. But I mean, if I talk about NMR, nuclear magnetic resonance spectroscopy, that's just a technique off the top of my head. People often use that data and can be really good at it. But the data they're actually looking at is actually quite highly filtered. So it's not unusual in science to be sometimes using, I think actually it happens a lot, you know, mass spectroscopy, for example. And that's probably highly filtered data as well. You never see the raw signal. So it's the same, it's pretty similar in electrochemistry, but we could probably start opening up that raw signal a bit more. Anyway, so we gather a lot of what's called forward and reverse currents, forward and reverse currents, forward and reverse currents. In this particular case with square wave voltammetry, and also the same with differential pulse voltammetry, in order to make the signal more specific, they actually do a subtraction. So you can actually record 2 peaks on a square wave voltammetry. You can do the forward, the backwards, or the reverse, I should say, and you can subtract them. So often in papers, what you're really looking at is the forward minus reverse, and then you get that black line. And when you see those black lines in a paper, it's often the difference or the subtraction of the forward minus reverse that you're actually seeing, because they say that the forward and the reverse both have a background component, but when you subtract them, you actually subtract the background component off, and you're only left with the true signal. I would say that, you know, I would say one thing, that reasoning actually works out that square wave voltammetry is more sensitive than cyclic voltammetry. It definitely is more sensitive than cyclic voltammetry. In fact, our sequence of events would be, when we're first starting an assay, we'll do cyclic voltammetry just to get a sense of where oxidations and reductions are taking place. And then when we've got that sense of actually we've got an oxidation reduction wave, we're going to do square wave voltammetry, but we'll narrow in on a narrower portion of the sort of potential window, let's say. So it does actually work. Now, differential pulse voltammetry is very similar to square wave voltammetry, at least in my opinion. It's again based on this idea that there's actually a digital staircase, except the waveform is a little bit different now. We do go up, but it's actually following this kind of waveform. So I'll just reverse that a little bit. So rather than kind of goes up, steps down a little bit, goes up, steps down a little bit. So it looks more like this. And there's again a component where you've got a forward and you've got a reverse. And again, it's basically filtering based on time because we're not taking the current in the entire pulse. And we're actually averaging the current that we do actually take. So it's kind of, it's filtered both by time and then averaging. And then you can end up with a, you can subtract those two from one another. And I want to say that the forward and reverse both contain a background component. But when you take forward minus reverse, you basically subtract the background and you're left with like a sort of a truer only the electrochemical component that you're actually left with. So question number 4. We at ZP, we do functionalize our pH electrodes to make them sensitive to pH. Those materials, I cannot reveal them, see, because then I'm sort of, I mean, we do have to keep some trade secret here. But I do not believe that they will leach, and I do not believe that they are toxic. But I have to, I have to make these kind of statements because I don't want these YouTube videos then being used to kind of say that ZP will sell products on its website for R&D purposes only, and they are not sold so that you can put them into medical products. People ask me to make declarations on that, and I cannot make declarations on YouTube that you are safe to use these products in our in medical products. I tried to give people sort of straight answers, but you've also got to understand that I cannot be making guarantees on things on a YouTube channel. So I think the risk is low for you. You cannot use this. You can buy these materials. You can do R&D on these materials. You can do leaching testing these materials. You can do all of that, but you cannot launch a company then and just start putting these products straight into that because it's a proper risk assessment has to be in place. So I think your risk is low. I think you can go ahead and do your lab experiments, but do not be then using this to inject materials into people. Question number 5. Diazinon is quite a nasty organophosphate. It's used in sheep dips to probably, I think, to take ticks or some sort of lice off sheep. It's probably used at quite high concentrations. I think maybe 100 nanograms per litre, and then when it gets into the water courses, it may be sort of 10 nanograms per litre. But they may be interested in testing it about 50 nanograms per litre. They've done a little bit of research on this. I've also done a bit of research on this. The first thing is that, I mean, people can do this, but when I bring this up is because if you want to know whether a molecule is intrinsically electrochemically active, if it's got an aromatic ring in it, and this has an aromatic ring in it, and it's got some heteroatoms in it, well, there's some heteroatoms here. Heteroatoms are often nitrogen, oxygen, sulfurs, phosphates. So we got some heteroatoms in here. So we got an aromatic ring, and actually the heteroatoms are also in the ring as well. We've got some phosphate groups here. Then this is giving me clues that this is probably electrochemically active, intrinsically electrochemically active. I did a little bit of a calculation on it. So just FYI, if they really want to do 10 nanograms per litre, I turned that into molar just to give me a sense of what that concentration is. It's in fact I realized I've just put an arbitrary 500 Daltons in here, so it'll be close to this, but this is approximately 20 picomolar. 20 picomolar is probably on the edge of things. What I mean by that is I was wondering if these people could test this molecule using an unfunctionalized electrode. But 20 picomolar may be on the edge of things. They may actually have to add some molecules or some materials or catalytic materials to make this sensor more sensitive, or make an electrode rather more sensitive. So we can do some back of the envelope. So first things first, this molecule is intrinsically electrochemically active. The kind of concentrations they're talking about, 10 nanograms per litre, 100 nanograms per litre is in here as well, and 50 nanograms per litre. These are approximately in the range of picomolars, tens of picomolars. So that's quite low concentration. Now, but I do, I always stand by this is an intrinsically electrochemically active molecule, and we can, well, I say we, it can probably, at some point, an assay can in fact be developed to run on either this potentiostat or using the electrochemical methods and the data pipe actually give you a concentration of that molecule. Now, I like my instincts sometimes because I was asked whether I thought this was, first of all, I was just told the molecule. I said, well, the molecule I think is intrinsically electrochemically active. That was my, just looking at the structure, and sort of, I want to say experience, and it is just experience basically. I haven't done any other calculations on this, but then I actually looked it up, and I would just want to this is not my work. I do want to quickly cite that this is from Professor Erdoğan at in the Faculty of Arts and Sciences at İnönü University in Turkey. I just want to make sure that you understand that this work is their work, but it's kind of useful for me, because I had the instinct or experience that this was an electrochemically active molecule. They show it is an electrochemically active molecule. They actually do it on I think it's a glassy carbon electrode with a Nafion coating on it. I got a suspicion. Nafion coating, by the way, is just it's a PTFE, a polytetrafluoroethylene with ionic channels in it. I could see that actually adding a little bit of specificity to this electrode. Actually, I think the PTFE will help with blocking other molecules and allowing this organic molecule to the surface. But they have, in the first instance, confirmed my suspicion that the molecule is electrochemically active. And also, rather interestingly, they've also gone for square wave voltammetry when they try to make the assay more sensitive. So all my statements earlier on about, well, you can use my potentiostat to, do square wave voltammetry use cyclic voltammetry to start with, but later on then you can use something like square wave voltammetry to kind of hone in on the sensitivity. These are genuine, these are backed up by this particular paper. This is what they're doing. In fact, I was going to make the statement. Yes, in fact, I can make the statement here, in fact. This paper, they say here they got a limit of detection of 75 nanomolar. So picomolar is 10 to the minus 12. Nanomolar is 10 to the minus 9. So they're about, and it's no criticism of the paper. It's just to say at this moment, this paper, let's say, is 1,000 orders of magnitude away from maybe what this end user needs. But what I found interesting, actually, and I'm just thinking aloud, is the signal is actually quite big. They have a big signal. So there's plenty of, let's say, headroom with the signal that they've got. And also, you can try a technique called absorptive stripping voltammetry, or absorptive stripping square wave voltammetry, where actually organic molecules tend to want to collect on electrodes, because electrodes often have if you choose, a carbon surface, especially a carbon surface with Nafion on it, they'll tend to be organic in nature, and organic molecules will enrich upon the surface, and then you can strip them off using square wave voltammetry. So in fact, I'm just thinking aloud here, by the way, there's definitely techniques for increasing the sensitivity. So confirmation that my initial guess is right. I like this question because, it's generally organophosphates are a problem in the environment. And I think people make these assays too complicated. This is a nice quick assay. Its limit detection, I agree, is 1,000 over what the maybe end users are looking for. But closing that gap, there are, you could think about ways of enriching the sample, and absorption is a way of enriching the sample. And so I could see us actually being able to translate assays like that onto platforms like this. Of course, super biased, but this is the beauty of this. In fact, I will have to do a demonstration in a bit about what I mean by that. Right, let's go on. Yes, because I thought I might actually have the word demo written up here, which will make me then actually do a demonstration. So let me do a demonstration just to show you that, in fact, we can do organic chemistry. Oh, sorry, the detection of organic molecules. This is not an organophosphate. I wouldn't even want an organophosphate in here. I'd have fume hoods, everything, you know. But let me just do a... But this demonstration is quite nice because it shows you that even though this is a potentiostat, we can do real-world applications on it because of something called the data pipe. But let me do a demonstration of this. I'm just going to give this a quick name. I'm just going to call that 42, tab 42. I'm just going to go to continue. I'll hit start in a minute. So let me just get the sample first of all. I'll put the sample on there. And I will hit start instrument. I realize that's now upside down for you. No, actually that's the way it ran for you. Right, so it's actually doing a cyclovoltammogram at the moment. This is because this particular sample is quite high in concentration, and it will process the data, and then I'll get a result on my phone, which I have got. So I have a result on my phone, but I'm also going to just quickly change screens for you. This is really important. See, I said earlier on we're data scientists. We're all data scientists now. Okay, so we're all data scientists now. That electrochemistry is a good means of collecting electrochemical data. Let me just sign in real quick on this. Oops, sorry. So every time I do an assay, the assay in fact loads up to a cloud system called Julie. I think this is the only electrochemical data management system essentially in existence. In fact, I can see my data there. So I can see the operator, I can see time and date up here, I can see the raw signal, and then boom, on my phone, when I hold that up to you, here is a result. Even though I've shown you the gathering of raw data in real time on the phone, we actually give people a real number. This is the power of the sensor potentiostat. The power of the sensor potentiostat is you can do all the electroanalytical techniques that you would otherwise love to do, but it's got a data pipe in it. And I've set up the data pipe in this particular demonstration to actually do this. It's got the cyclovoltammogram. In fact, it's done 2 CVs. On the second CV, it's processed the data, it's looked at the peak height, and it's turned the peak height into concentration. And that's what I send back to the phone. Most academic research gets stuck at technology readiness level 3, which says what we have proven is that we can do this in a lab. In order to make an impact, you have to be able to show it at technology readiness levels higher and make statements like proven to work in the field. Well, the reason you can't do this mostly in the field is because the instruments that you've got are very lab tied. And even if you do have the instruments, you then have a raw signal and a calibration curve. By the way, you notice I did no calibration. The reason I did no calibration is ZP is the only producer of screen printed electrodes that are coming onto the R&D market that are so reproducible that you can actually develop assays on them that don't require calibration. Now, if you are functionalizing those electrodes with pipetting, etc. in your labs, you are adding a manufacturing variability that is outside ZP's control. But the fundamental electrodes that ZP ships are very repeatable. Why? Because we have a feedback loop built into our business, which is we make them, we use them in our products, and by the way, we have to sell them to you. But the fact that we make and we use means that the feedback loop and quality is built into our business model. So I didn't need to calibrate that. That's really important because it really helps to get assays out the door and onto the market. And I'm just going to turn off this for a second. I'll just turn off myself just for a second. I'm just going to turn this on for a second. I'm just going to talk about the data pipe. So we were able to turn raw cyclovoltammetry into a actual concentration. Now, how do we do that? Because every time the sensor or potentiostat works, it sends its data to the cloud. we've set this cloud up so that it actually does, it filters data. So we've done what's called a low pass filter, though I've got loads of filters in here. It's flipped the data around the y-axis. That made it easier. We cropped the data, so we went and looked in a particular window of potential. And then we actually said, go and find the peak height on the reverse scan in the window centered at 250 millivolts, plus or minus 300 millivolts, and fit it to this formula. Oh, and by the way, the sample was diluted 10 times. So I told it where to find the data, what equation to fit it to, what my dilution was. And because of all that, it meant that this end user wasn't left with cyclovoltammetry, which is where every scientific paper ever leaves anyone with, or not cyclovoltammetry, but some sort of electrochemical technique. It actually sent back the final concentration. And that's why I say we're all data scientists now, but we're just not taking the final step, really, which is actually processing data and turning it into concentration. We do it on Excel, and we do it, we even in Python code now. This is the only potential stat that has a data pipe built into it through its cloud system that'll actually take your peak height, put it through the algorithm. Peak height was 4.943 microamps, and turned it into a final concentration. And that is a very different style of potentiostat. So that was the demo. So theoretically, we could also do that for these organophosphates, and I think that particular compound is one of the targets that we could otherwise do. So it's a pretty powerful technique. Any of these kind of techniques can then be used in conjunction with that data pipe to essentially translate the assay out of the lab and onto the market, or at least into the hands of real users. Question number 6. I'm probably more focusing on one of our gold electrodes here. We do a lot of this at ZP these days. There's a lot of interest in molecular assays, be it DNA or RNA based. But in those kind of assays, there's often a hybridization with you've got a capture strand. Sometimes, you call it capture strand, and it's capturing its complementary strand. I quite like molecular assays. The cleverness that you can actually get specificity by the order of which you've got these bases. It clearly works. I mean, that's why we it's the sort of blueprint of life. Let's say really thanks to nature again, I would say. But anyway, you get a specific hybridization, and if you want to know if that hybridization has taken place, you can do it in the presence of something like a Maldala blue, one of these dyes. So there's a whole bunch of dyes out there that are electrochemically active. Maldala blue, if you look that up, things that are structurally similar to that, they can actually intercalate. So when you've got a hybridization like this, you've got grooves in the double strand of the DNA, for example, and these things will actually intercalate. And the more hybridization you've got going on, then the more intercalation you've got. And actually, if you were following this by square wave voltammetry, for example, then the current would increase proportionally. So if you are building a molecular assay and you want a simple way of doing it, I'm not a great fan of gold. I quite like carbon, but you can do self-assembled monolayers on gold, or you can also use a molecule called pyrene NHS on carbon to activate your surface, and then you can attach your hopefully then attach your capture RNA or DNA to that surface. Having done that, when you then add your target, they should hybridize. If you want to know whether it's hybridized or not, adding a molecule like a Maldala blue that can intercalate is a way of, first of all, knowing the hybridization has taken place, and the amount of intercalation and therefore enrichment of that Maldala blue near the surface is an indicator of the amount of hybridization you've got going on for the amount of target, for example, DNA that you had in that sample. Question number 7, we just had some questions about lactate sensor. So we do lots of videos about lactate sensors. I don't want to, maybe I'm already boring you, but I don't want to overbore. I don't want to go on too much about it, but we do them. And we do them in a wire format. I'm just going to turn myself off for a short second here. So here I go. And we do them in a wire format. And we've just been testing recently, and we've been testing up to 12 millimolar, which actually works. I think maybe in a sporting exercise, maybe going up to 20 millimolar, but most people at rest should be at 0.5 to about 1 millimolar. And so we've got a good way of actually showing that somebody is either they've got excess lactate because of some sort of metabolic breakdown, but some sort of metabolic issue going on here, or it's demonstrating that they've actually been exercising. So we do have lactate sensors in a transcutaneous manner. I should actually say that probably that webinar on the 5th of November on wearables would be probably interesting to people who may be otherwise interested in lactate. We were at a conference the other week. There was some data was put up about glucose sensors. I have talked about a lot about glucose sensors on our on various videos. I'm not going to go on about it now, but I think a lot of glucose sensors are coming to the market, either what's called Gen 1 or Gen 2 glucose sensors. So I'm not going to talk about that mechanism so much, but I just not starting to begin. I have been very interested in Michaelis Menton kinetics for a while. And so when somebody shows me data on a slide at a conference, you know, and even if you just show me the, let's say, the current, we can actually have a, you know, we can synthesize from that current what this sensor is actually doing. So glucose sensors, this is a very simplistic Michaelis Menton treatment of a glucose sensor, because a glucose sensor actually has a third part in here, which is often its mediator, which is oxygen. But if I was just treating it as an enzyme with its substrate, then it's got kinetics. But enzymes are not just binding with their substrate, they're actually catalyzing a reaction. In the case of glucose, glucose is binding. It's oxidized to glucolactone. It hydrolyzes very rapidly, by the way, glucolactone to gluconic acid, but that's secondary chemical reaction after the primary enzyme reaction. So I don't include it in my treatment here. But it's just to say that I was at a conference, I saw somebody's current versus time, and from that it's enough to then, if you make some simplistic, and I'm using the word simplistic, assumptions, you can actually back calculate how those electrodes are behaving. So that's what I've actually been doing. That's why I like the fact that I did Michaelis Menton when I was an undergraduate, but even to this day, it actually, that's a beautiful thing about bioelectrochemistry. It still works. So Michaelis Menton describes the movement of substrate to product through an enzyme reaction. It describes that the rate at which that reaction takes place is often proportional to the substrate concentration, but there's a point at which you basically start losing enzyme activity, or the amount of enzyme activity versus the number of substrate starts becoming a limiting step. In the sense of glucose oxidase, there's also another contributor, which could be oxygen limitation. With all that said, if you're following Michaelis Menton kinetics, you can essentially have something called, when you follow a sort of an equation where it's Vmax times substrate over Michaelis Menton constant plus substrate. You do see people deriving this online. Deriving it is, none of them are actually solved this. This was derived, by other people, let's say. But this V here means this V here. So we can, for any substrate concentration, we can sort of effectively figure out what the rate of reaction would be if we just knew the Vmax and the Km. The Km is a good indicator of it's really the half Vmax, but it's also an indicator of where you would actually find that sensor to be quite linear. So I've got to be careful with this statement. You can have too much Vmax on a glucose sensor and end up basically consuming too much glucose and producing too much hydrogen peroxide, or consuming all the oxygen in a particular system. So you can end up with too much Vmax. But you want to, I sort of tend to want a high Km, because a high Km tends to give good linearity, makes the maths a bit simpler. But having been given, let's say, for example, I was at this conference and I saw somebody's current at 11 millimolar concentration for a particular sensor, and I think I just approximated here that they are like at 100 nanoamps, and then after about 1,000 hours it started to disappear. I'm just saying, when you know the background bioelectrochemistry behind these things, you can actually sort of figure out what their current versus concentration probably look like on that particular sensor. And in this particular case, the sensor was quite stable, and so these are all sort of me looking at the Michaelis Menton, using the Michaelis Menton to figure out what I think their sensor probably looked like. And then at the end here, they kind of have an end of life kind of event where the signal changes dramatically, and that's when the essentially the Michaelis-Menten equation has also predicted a very different kind of sense. So in fact, they probably have okay linearity, but in fact it plateaus off much earlier on. So the take home here is you can get to a stage in your understanding of your bioelectrochemistry where in fact it's just enough to see, you know, a glance at some sort of signals versus time, and then if as long as you understand the underlying kinetics of these kind of systems, you can therefore back calculate what the sensor would have looked like, the sensor behind these actual data points. So I found that kind of interesting to apply Michaelis-Menten in that particular case. So multi-analyte detection, super simple. These are all comprehensive metabolic panel members, so we didn't take too much to say that they're all quite achievable. Generator, collect, and mode for IDE. I spent something like 10-15 minutes answering that. The quick answer is, if you want control on both working electrodes, working electrode 1 and working electrode 2, the Anapod EIS will not do that. But in fact, I gave you a scenario where in fact it would work, but you have to look to those notes. Linear differential pulse voltammetry. There's a lot of filtering going on in linear differential pulse voltammetry. The filtering is all set up to actually give you the best electrochemical signal that you can have. The filtering that's going on is actually its timing, its averaging, and its subtraction. So there's actually three things going on, but then in the end you get a more sensitive signal. Something I didn't say actually is I actually prefer square wave voltammetry these days over differential pulse voltammetry, but they're very similar, to be honest with you. pH sensors, what nasties do we have? I don't think we have any nasties, but I can't go any further than this. I don't want to be pulled into a legal dispute, let's say. I do not want you using these on real products, and I think your risk is low, but I do not want you using these on real products. You really do have to have a proper agreement with ZP, and we will only do it with really well-funded startups or serious companies, let's say, who are well-funded. Detection of Diazinon. Diazinon. I'm keep trying to get the pronunciation on this. I think you can do that actually on our sensor or potentiostat. In that particular academic paper, they got down to 75 nanomolar. You need more like 25 picomolar. So that's an order of magnitude away. But I still think you may have some capability of doing it, but it will take a bit of work. I would definitely say that. Let me go back to the questions just as I sum up here. Intercalation assays. So what I mean by intercalation assays, this is a good way of, if you've got a molecular assay based on hybridization, then using something like Meldula Blue, which will intercalate and enrich on the surface, and you use something like square wave voltammetry, then you can have a signal versus that hybridization and therefore that intercalation. Lactate sensors, we've just been testing this week and we did get up to 12 millimolar, and glucose sensors. One thing you could take away from my quick spin through is Michaelis-Menten works quite well for glucose sensors, even though it's oversimplified what I just did because I left out the oxygen, and I can be criticized for that. But it allows me just to get a sense of what those sensors look like behind the signal that's behind the numbers that were given. You can actually work back and actually figure out what these sensors actually really look like. I think quite useful. Right. If you've got any questions of ZP, don't hesitate to reach out to us. I'd love to know how long I've actually been talking for, but probably too long. Okay, any questions, don't hesitate to reach out. Okay, thanks very much.